We've been looking at the general eigenproblem, getting eigenvalues and eigenvectors of a general matrix A. We've discussed the approach, we've discussed applications, we've looked at a number of examples, and now we want to focus on a specific special case. It's a special case that involves real symmetric matrices, and the reason is because these arise in a number of applications that we care about as scientists and engineers. So we'll look at the properties, we'll look at some examples and applications of that, but it's a helpful context in which to introduce the ideas and the method by which we do the diagonalization. So in terms of some of the applications, we've seen in mechanics where stress, strain, moment of inertia tensors, which are just matrices, they are symmetric. The Hessian matrix, which we're going to see in chapter 4, essentially it's all the possible second derivatives of a function, say u of x, y, z, however many variables. If the function is smooth, then it turns out that the Hessian is symmetric. In other words, mixed derivatives, it doesn't matter the order in which you do the differentiation, whether it's x first then y or y first then x if the function is smooth. So that means that the Hessian matrix will be symmetric. In part 2, we're going to focus on numerical methods, and some of those numerical methods naturally produce real symmetric matrices, and we could take advantage of some of these facts and properties there. Also, I've mentioned proper orthogonal decomposition a few times so far, and I keep pointing ahead as an application. There's a particular matrix called the Covariance Matrix that is very important within the context of POD, and it turns out the Covariance Matrix is also symmetric. So there's a lot of applications where we have real symmetric matrices, so we'd like to know if there's anything special about their properties. So we have a real symmetric matrix A. So what that means is above and below the diagonal, the corresponding elements symmetric around the diagonal are the same. Formally, that means that A and A transpose are the same. Of course, it has to be square in order for it to be symmetric. We're also going to add the additional requirement for now that the eigenvalues are distinct. So they're different. So let's take two eigenvalues of A. A could be any size, and let's just take two of them, lambda 1 and lambda 2. And we'll consider the eigenproblems and see what we can learn about the eigenvectors if indeed the eigenvalues are different, they're distinct. So we write down the two eigenproblems. AU1 is equal to lambda 1 U1, and AU2 is equal to lambda 2 U2. So let's take this first one, and let's take the transpose of it. So if we take the transpose of both sides, on the left-hand side we have the transpose of the product. Remember, the transpose of the product of two matrices is the product of the transposes in reverse order. So in this case, that means we have U1 transpose times A transpose. Then I'm also going to post-multiply both sides with U2. So U2 on the left, U2 on the right. All right, so we'll set that aside for a moment. So now let's take a look at the second of our eigenproblems. AU2 is lambda 2 U2. So let's pre-multiply U1 transpose on both sides of that. Now what you'll notice is if you compare these two results, the left-hand sides are the same because A and A transpose, if A is symmetric, those are the same. Therefore, if I subtract one from the other, the left-hand sides cancel, and I'm left with, from the right-hand sides, lambda 2 minus lambda 1, so the difference between the two eigenvalues, times U1 transpose times U2, and that has to be equal to 0. Well, U1 transpose times U2, that's just the inner product of U1 with U2. Now we've already said that the eigenvalues are different, they're distinct, so this product is not 0 because of the values of the eigenvalues, so it has to be 0 because this inner product is 0. If the inner product of U1 with U2 is equal to 0, well, what does that mean? That means that they're mutually orthogonal. So for a real symmetric matrix A with distinct eigenvalues, the eigenvectors are mutually orthogonal to one another. Very powerful result. So we've summarized that here. I've also added in the fact that eigenvalues of a real symmetric matrix are real. I'm not going to prove that here, but that turns out to be the case as well. So this is why in our principal stress, principal axis problem that we did 2 videos ago, you'll remember that because the stress tensor was symmetric, which it has to be from physical considerations, we determined the eigenvectors, and they so happen to be mutually orthogonal. Well, now that we see that they actually had to be, because it was a real symmetric matrix with distinct eigenvalues, so therefore gave us mutually orthogonal eigenvectors, which are the principal axes, which have to be orthogonal. So that all makes sense. The physics and the math all make sense. So that was the case with a real symmetric A and distinct eigenvalues. What if we have real symmetric A with repeated eigenvalues? This case, there's some confusion about, and I'll try to clear that up here, and we'll do an example in a later video which illustrates what I'm about to say. So the confusion comes because what a lot of people will say is, if you have a symmetric matrix, the eigenvectors are mutually orthogonal, and they don't make a distinction between distinct or repeated eigenvalues. So what's happening here is, as we just proved, that is true, that statement is true for sure if the eigenvalues are distinct. If they're repeated, it's not that the eigenvectors must be orthogonal, it's that you can choose the constants when you form your eigenvectors such that they really are mutually orthogonal with the others. So any choice of the constants won't necessarily be mutually orthogonal. They will be linearly independent, but not mutually orthogonal. But you can make choices such that they are. So it's a bit of an overstatement or oversimplification to say that all symmetric matrices have mutually orthogonal eigenvectors. However, you can arrange it so that that is indeed the case. So just keep that in mind, and when the time comes, we'll illustrate that distinction. So what we're going to do in the next couple videos is look at 2 applications. The first is solving systems of linear algebraic equations. So that was the main topic, the main subject of Chapter 1. So we're going to show how this property that we just derived can be used to devise an alternative way to solve an AU equals B if A is symmetric. The second application is to what are called quadratic forms. When you think of quadratic, you think of something squared. So quadratic forms, I'll introduce them, we'll talk about what they are and what they represent and where the applications are. And within the context of that application, quadratic forms, I'm going to introduce a process of diagonalization. And then again, we'll broaden that later on, but it's a good geometric, intuitive context within which to introduce the ideas of diagonalization.